All right, hi everybody, welcome to the chapter 1 to 3 final exam review. This is going to cover topics in chemistry, the central concept, from chapters 1 through 3 as part of a final exam review for the end of our first semester. Remember that we will go all the way up through chapter 11, and this is going to go through by topic based on the topics list you wrote from your chapters in the book. Okay. All right. So without further ado, let's get started. In section 1 of chapter 1, very first thing you're asked to do is to explain the difference between matter, atoms, and molecules. For reference, matter is literally defined as anything that has mass, takes up space. Okay. From there, we then further define it using terms like atoms, elements, and molecules. An atom is a single unit representation of a piece of matter. A molecule is two or more atoms combined. They do not necessarily have to be different types of atoms in order to be considered a molecule. So for instance, down here, we also have how molecular models work and understanding representations. This oxygen molecule has two atoms of oxygen bonded together, so it is considered a molecule. Down here, we have a water molecule that has an oxygen atom with two hydrogen atoms attached to it, and so on and so forth. So these are all representations of atoms, and one of the things that your book really wants to make sure you understand is how you use those representations to represent different molecules. All right, section 2. Apologies, I'm having some trouble getting my computer to respond. In section 2, you're asked to discover or describe the differences between gases, liquids, and solids. In general, the rules are that solids are highly ordered. Over here on the right, you see ice is a highly ordered solid. Our molecules are compact. They are organized in specific patterns in order to fill as much space as possible. In liquids, we see a little bit less organization. The molecules are supposed to be a little bit looser. Remember that water and ice are a little bit different because water is weird. And we've talked about that in many different chapters, but this chapter is no exception. But liquid particles are generally a little bit further apart, not very far apart, and are going to be a little bit less ordered. They tend to be able to flow, which means they are able to kind of adapt their shape, which is a very cool property for a lot of them to have. And then gas particles are going to be the ones that are the farthest apart. Over here on the far left, we see our gas particles in this model substance of water. They are far apart, they're kind of moving pretty fast, and things like that. Remember that temperature-wise, usually the solid version of material is going to be the lowest temperature, and the gas version is going to be the highest temperature, with liquid somewhere in the middle. Next, you're asked to distinguish the difference between elements, compounds, and mixtures. Over here on the left-hand side, we have these two boxes, box 1, box 2. Those first two boxes are actually an example of both an element. So this is an element. And then this one here is actually both an element and a molecule, because it has more than one atom, and because it also has multiple atoms in it that are identical. Because they're identical, it is an element, but because there's more than one, it is a molecule. Over here, number 3, we see an example of a compound that has different types of atoms bonded together. 2 or more is the rule when compounds come down to it. And then on the far right, we see a mixture of all of the different types of substances from the previous 3 boxes. We see elements, we see molecules, we see compounds, etc. The last subject in section 2 of chapter 1 is to identify atomic symbols of elements. And so I kind of just put up an example here of what information we can find from a periodic table symbol. Remember that element symbols are actually the same thing as atomic symbols. It's a letter that represents the actual element itself. Okay, next up is chemical and physical properties. So physical properties are things like density, shape, whether it is able to be ground into or whether it's able to be melted and pulled into a wire, ductility, and conductivity. Those are all more physical properties. Chemical properties would be reactivity related. So does it react with nitric acid to form a new substance, etc. Then we have intensive and extensive properties. Remember, with our intensive and extensive properties, we're looking for the fact that intensive properties do not depend on the amount of sample present and extensive properties do. So our intensive properties are amount independent. And our extensive properties are amount dependent. Another physical property that we can kind of keep an eye on is what color is the thing, at what temperature does it melt, what temperature does it boil. Chemical properties, like I said, is more about reactivity. Okay. With our chemical and physical changes, one of the things I like to remind us of is physical changes are ones that can be reversed. Whereas chemical changes are ones that change the material and you cannot put it back without having some kind of condition. So for instance, when we're looking for signs of a chemical change, we're looking for gas production, color change. Maybe we're looking for the generation of heat or light, etc. Okay? Remember, not reversible. And then very last, we have a couple of different separation methods. So the separation methods discussed were filtration, where we use the properties of the substance to pick the best separation method. So for instance, if we're trying to separate like sand from water, then we may use like filter paper. If we're trying to separate two different liquids, maybe we choose distillation. Distillation is the process by which we can purify a liquid by exploiting its boiling point. Chromatography is one that involves the movement of liquid using capillary action up a piece of paper or some other special paper in order to separate materials based on their molecular weight. Okay. Next up is energy, heat, and work. We already know a lot about energy, heat, and work, but in this particular case in chapter 1, we're trying to remind ourselves that energy is going to be the capacity to do work or transfer heat. Work is something we talked about in several chapters in this semester, but essentially work is related to the displacement of an object. Whereas heat is more transfer that causes a change in temperature. Okay. Later on in chapter 5, I believe, in thermodynamics, we talk more about how kinetic energy and heat are essentially treated the same. But in this particular chapter, you are introduced to the formulas for both kinetic energy and potential energy, gravitational potential energy. Oh, whoops. My bad. Oh my gosh, stop it. My PowerPoint is hateful. And these are going to be used to make sure that our calculated amount of energy is something that we can monitor and or determine. Chapter 1 gets closer and closer to the end of Chapter 1. We use units to kind of describe how different energy transfers can take place, and or we use units to kind of describe the other types of things going on in different chemical reactions. So the 7 base units are ones that we discuss for a reason, because we need to be able to use those SI units when necessary. So for instance, for energy, the SI unit is the joule. For length, it's the meter. For mass, it's the kilogram. For temperature, it's the Kelvin, which down here we're actually going to talk about the fact that if we want to convert to Kelvin, we're going to use the delta C. So Celsius plus 273.15 means equals Kelvin. Others are time, which is in seconds, and the amount is the mole. And there's a couple more, but these are the ones that are actually the most important for our particular semester and for our particular class. So these are the ones that I need to make sure you know. Metric units and derived units are a concept that involve the... Oh, I'm sorry. I will not have you doing Fahrenheit to Kelvin on your quiz, but know that there is a way to do it. For us, really, we need to just be able to do Kelvin to Celsius and Celsius to Kelvin. Metric base units would be like if the length of something is measured in meters, then area, which is what we call a derived unit, is length times width, which would end in a unit of meters squared. And volume is another derived unit, which is length times width times height, has a unit of like meters cubed. So derived units are ones in which we take the metric base units and we multiply them. Conversion of these things is also going to be something you're going to be asked to do. So if I tell you that there are 1,000 grams in 1 kilogram, and then I ask how many kilograms in 375 grams, you're going to set up your math to get this done. Okay. Energy quantities in joules, it's so if you go back to that kinetic energy equation, mass times velocity squared will get you a unit of joules. Okay. All right, next up is uncertainty in measurement and significant figures. So in order to describe this one, we have to be able to describe precision and accuracy. Precision is specifically related to sig figs, whereas accuracy is related to true values. So if we're trying to do some kind of math that proves that something is correct or not, or is, let's say that like a value we got from lab is the same as one that is reported in a paper, then we're using accuracy or accuracy values and or methods to describe that, versus precision, which is trying to describe how close to ourselves we were and how accurate we were in our measurement during the fact that we did some kind of a measurement. Exact and inexact numbers are exactly what we're talking about with sig figs. So sig figs go back to all 3 of these topics today. But if I say that the time was reported at 1.37 seconds, that is an exact number. If I say the time was 1/3 of, say, a quantity like pi, that is an inexact number. Or if I say something is the square root of 3, that is also an inexact number. I'm giving like a summarized version of the number. Last is sig figs, exponential notation, SI units. So sig figs, remember your rules. I would highly recommend that you go back through that if you do not remember it, but you will be asked questions about sig figs, and you will be asked to do equations and calculations and report sig figs on your final exam, so do not forget the rules. Exponential notation is scientific notation. Hopefully you feel pretty confident about using these when we use them. SI units and calculations, it's just carry your calculations through. So for instance, if I'm doing like a density calculation, which is mass over volume, then my mass or my volume should be in those specific units. Now, sometimes we obviously get different values. Sometimes we've also reported our densities in like grams per milliliter because it makes more sense on the bench, but SI units would say the density needs to be in kilograms per meter cubed. All right, last but certainly not least in chapter 1, and you'll notice that this is going to happen in some of our chapters in today's video. You're going to have some of these topics that you've written out. You can cross them out if I've crossed them out, because it means that it will not be on your final exam. When we say conversion factors and being able to use derived units to go to an answer, think about something like if I ask you how many miles per hour is a car moving if it moves at 30 kilometers per second. Okay, so if I'm asking you something like that, then I'm also asking you to set up a conversion. 1.609 miles, I believe. Oh, you know what? I think I flipped this. It's 1.609 kilometers because there are fewer miles in a kilometer. And then there are 3,600 seconds in 1 hour. So be able to do those dimensional analysis type problems. That's what that is implying in section 7. Okay, moving on to chapter 2. All right, the postulates of Dalton's theory are over here. Some of the famous questions that are asked about this are things like, which of the following is not a postulate of Dalton's theory? And then it'll say something that doesn't match one of these 4 things. We talked about these at length, and I would highly recommend you know them, but don't spend hours trying to learn them, right? Kind of keep it in the back of your mind, read them over a couple of times and make sure you understand what they're saying. Dalton is one of the first people who actually writes down atomic theory and kind of has like a whole, hey, we should write this down, we should communicate this with people. Now, are all of his theories correct? They are not. Some of them are wrong. One of the things that we actually pull from Dalton's atomic theory is the 3 different laws of conservation of mass, constant composition, and multiple proportions. So, law of conservation of mass says that mass present before must be equal to mass present after a reaction. Apologies. Okay, the law of constant composition says that if we have a compound of a specific kind, the number and types of atoms is constant. In other words, if I have ibuprofen is a chemical, right? Like it's a pharmaceutical formula. If I take that here in the United States, if I find the same thing overseas and it's called ibuprofen, then I should assume that it's the same exact formula as the one that I've taken in a different country. The law of multiple proportion says that when these things combine, Whoa. I don't know what happened. Apologize. Atoms join in whole number ratios. Whatever. So when if I'm gonna have a compound, it's gonna have whole numbers, not halves. Okay? Oh, hello. Okay. All right. The experiments that led to the discovery of the electron and the charge. Okay, so you know the 3 experiments. We've talked about them before. But the 3 experiments that led to the discovery of the electron and its charge. First is the cathode ray. Second is the oil drop. No, I can't. And last, but certainly not least, is the gold foil. Rutherford's gold foil. The 3 of them proved collectively that there was a nucleus in the center of the atom, and that there were these negatively charged particles called electrons floating around on the outside. What the size and charge of those electrons are was also determined using this. Okay. Then there is this section on radioactivity. I'm going to have you actually cross this one off. This section talks about the difference between alpha radiation, beta radiation, and so on and so forth, but it's kind of outside of the scope of this semester. We will talk more about it next semester. The nuclear model of the atom is the one that we now all adopt. So it puts the protons in the middle, puts the electrons outside in a cloud. Remember, they can kind of be anywhere. And so on and so forth. Okay. Next up is going to be relative charges and masses of protons, neutrons, and electrons. So over here is the chart from your book that I highly recommend you look at. This chart aims to kind of describe to you the fact that a proton and an electron are equal and opposite charges, one positive, one's negative. And not only that, but the mass of a proton is 1,000 times greater than that of an electron. So they're equal and opposite charge, but an electron is much smaller, which is why it can move so much faster. The second thing I want to kind of point out to you is this paragraph in your book. This is from your textbook on what actually holds atoms together. I want you to read this, and I want you to make sure you understand what it's saying about strong nuclear forces. These are the forces responsible for keeping protons and neutrons in the center and electrons on the outside of an atom. And I think it's important that you are able to describe this. We also drew diagrams in class, or we saw diagrams in lecture, where we had electron here and electron here, and this is a repulsion, and then proton here and electron here. This is an attraction, right? So there are a couple of different ways to go about this, but I recommend you understand what's actually written in this paragraph, because it's the way to describe how these forces are actually holding an atom together. Next up is isotopes. So here's an isotopic symbol. It obviously has the atom itself. It has the mass number, which is protons and neutrons added together, and then it usually has the atomic number of the atom on the bottom. Okay, in order to determine how many protons, neutrons, and electrons this thing has, I'm going to take this information, and I'm going to assume, since there is no charge, that my electrons, must equal my protons, and that my protons minus, P plus N. So my mass number minus my atomic number will equal my neutrons. So mass number minus atomic number equals how many neutrons I have. I'll remind you that you did a few of these on your different assessments, one of which was a chart in trying to determine how many protons, neutrons, and electrons each thing had. Okay. Next up is the trying to figure out how this isotope thing comes in to actually describe and the atomic weight on the periodic table. So this is where you say you have 95% carbon 12, and then you have 5% carbon 13. When you try to figure out what the total mass is, and your mass is something like 12.11, okay, like that of a carbon atom, or 12.01, sorry. Then we say that, this is the average atomic weight based on isotopic abundance. I would recommend you look at your chapter and at your notes. We've done some math for these, and there was kind of a process where you multiplied your mass times your percent abundance after you had divided it by 100. Then you add them all together, and that gets you your total weight. For that particular thing, it's the same thing here as it is down here. So these two things are kind of related to each other, 2.41 and 2.42. Converting between atomic weights and isotopic abundance is, I'm not going to make you go backwards. I may ask you to do isotopic abundance to atomic weights, but really what these two things are just asking you to do is take into account the fact that the atomic weights on the periodic table are a function of what's present and how much is present, what abundance is present for each different kind of isotope of each different atom. The last two on mass spectrometry you can cross out. All right, next is general properties from locations. So when we look at, say, elements in group 1 on the periodic table, what we're asking is, what are some properties they have in common, okay? And from class, we talked about the fact that these are, so maybe from group 1, these are the alkali metals. So they are soft metals that conduct electricity. They are also reactive with water. We can just say reactive, based on where they're located. Okay. Then let's say I give you a halogen, so like chlorine, which is in group 8. Then using that information, the fact that it's a halogen and it's in group 8, I'm sorry, not group 8, group 17, you can say things like, okay, this is reactive, but it's a nonmetal. It's made up of nonmetals. Looking at the periodic table, you'll also see that the halogens have every single type, so metals, nonmetals, and metalloids in them. Some of the other groups on the periodic table have different types of properties. You're looking for general statements, right? So general statements. Overall structure of the periodic table, when it comes to periodic table geography, hopefully you feel pretty comfortable. You know, for instance, that this is all metals. Then there's the semi-metals or metalloids. Oh my gosh. Sorry. Here we are. Semi-metals or metalloids. Then we know up here are our non-metals. You know that as you go across, these are periods. You know, as you go down, these are groups. General periodic table geography. You know where the S block is. So S, this is D, this is P, and then down here would be the F block. Things like that are going to kind of continue to build throughout our chapters. But for now, that's kind of what you need to know about the periodic table geography. All right. Given a picture of a structure, so think like methane, you should be able to write a compound formula. So for this one, we would write CH4. For this one, we would write H2O2 or O2H2, doesn't matter. For water, we would write H2O. So basically taking the individual atoms and writing out an actual compound structure. Molecular and empirical formulas, just kind of differentiating for this one, there's like C2H4 is a molecular versus its empirical would give us the lowest common denominators of all of the different atoms. So since we could divide everything by 2 in C2H4, we get CH2, and this is our empirical formula. And this one must be molecular. Okay, hopefully you can kind of see where this is going. We are going to be able to go forward and backward when it comes to empirical and molecular formulas using the mathematical process that has been discussed previously. But for now, just kind of understanding how these work. Okay. All right. So this one, next section kind of focused on common charges for ionic compounds. So remember, ionic compound is a metal plus a nonmetal. Okay, and based on their locations, there are different formulas. So things in group 1A are +1, things in group 2A are +2, things in group 3A are +3. Remember, 4 can be plus or minus 4. 5 is -3. 6 is -2. And 7 is -1, and then group 8 doesn't participate. Okay? So knowing those common charges, we can do predicting the most common ionic charges. So for instance, an atom of sodium, most common charge is going to be a +1 because it is located in that first group, etc. Okay? Oxygen's most common charge is going to be a -2 because of its location on the periodic table, etc. Okay. Empirical formula of an ionic compound given different elements. So if I said form an ionic compound with magnesium and chlorine. Okay. Well, you would know that magnesium has a common 2+ charge. Chlorine has a common -1 charge. In order to form their compound, you crisscross them and you get MgCl2 is your most common. Okay. All right. Molecular and ionic compounds. Remember, metal plus nonmetal makes it ionic. Molecular is 2 or more nonmetals. Most common types of molecular compounds are carbon, hydrogen, oxygen containing compounds. They can have any of those things in them. Another common molecular is going to be like, anything that has 2 or more nonmetals. Okay. Name an empirical formula. This is going to involve like, okay, so sodium nitrate. We know sodium is Na+, we know nitrate is NO3-. We crisscross. You'll notice most of these are actually crossed off. You do not need to know the inorganic acids. You do not need to be able to do anything with the organic things. This is a, hey, if I gave you a simple compound like magnesium chloride or magnesium bromide, be able to use the charges. So for instance, that magnesium is always a +2 based on its group location, and bromine is always a -1 based on its location. Be able to use those things to get yourself a compound. The basics, not trying to make it more complicated. Okay. All right. Last, but certainly not least, is chapter 3. This video is going to go through the end of chapter 3. There is a few things in chapter 3 that I won't go over just because it's not going to be on your quiz, or I'm sorry, on your final exam. But for this particular case, we're looking at law of conservation of mass. This chapter is going to deal with stoichiometry. So we're going to introduce stoichiometry. We're going to look at the different ways that we have to do it. And we're going to use some of that information from the periodic table to actually determine what does it mean to do stoichiometry. In order to get there, we have to be able to talk about chemical reactions. So when we write a chemical reaction, we have to make sure it is balanced. Coefficients must be appropriate for the balancing. The reason we do all of this is because of the law of conservation of mass. The law of conservation of mass says that things on the left side have to equal things on the right side. Reactants and products must be equal as far as number and type of atoms. So for instance, I cannot have like Na plus O2 makes H2O or N2O, because those are not the same things. There's no nitrogen, and nitrogen and Na are not the same thing. When we balance chemical equations, remember we're watching our coefficients on both sides of the reaction. The next section of chapter 3 kind of discusses different types of reactions. So combination reactions are like synthesis. Decomposition is breaking apart. Combustion reactions have 3 things that are in common. Okay, identifying them and being able to predict what's going to happen if they're actually going to occur the way they say they are is going to be one of the skills that will be quizzed on this particular test. All right, formula weight from empirical formula or molecular weight from molecular formula, both are done the same way. So if I give you CO2 and I say, what is the formula weight of CO2? You're going to tell me, oh, I can find that using the masses from the periodic table. Carbon is a 12.01, oxygen is a 16, and there are 2 of them. It's going to give me a mass of 44.01 AMU. And later on in this chapter, we'll also say that we can say that's equal to grams per mole as well. So this is our molar mass or our formula weights. They are identical, except that their units are different. The process to calculate them is identical. Their units are just the different ones. Elemental composition by mass from empirical or molecular formula means like if I have the CO2 from before and I want to know what percent of CO2 is carbon, and then I'm going to take my mass of carbon, I'm going to divide by my total mass, I'm going to multiply by 100%, and I'm going to get a percent of carbon. Oops. And I can do that for any compound as long as I have the molar mass of the compound, which I can get as long as I have access to a periodic table, which of course I always do. Molar mass for a compound is just going to be literally using the same process as formula weight and just change the units to grams per mole, like we saw on the previous slide. Grams, molecules, and moles, this is where Avogadro's number comes in. So 6.022 times 10 to the 23rd atoms is 1 mole of atoms. I'll remind you that there are several different kinds of conversions we can do. If I say, how many grams or how many moles of O2 in 35 grams of O2. Then I'm going to take my 35 grams of O2. I'm going to divide by the molar mass of O2. 16 times 2 is 32. And then I'm going to get a number, 1.10. I estimated. If you check it and it's wrong, don't let me know. So these types of conversions, right? So now if I said, how many atoms are in this number of moles, then I'm going to multiply by Avogadro's number. Oops, apologies. Or molecules in this case, because O2 is a molecule, not an atom. Apologies. Okay. Then you can find how many molecules there are. Now, let's say I want to go from moles to grams. Then I need to multiply by a molar mass, etc. Okay. This next one involves using percents in order to determine what an empirical formula is. I will remind you that this is a task that you need to be able to do. I will put one up here for you guys to practice. Just 1 second. I'm going to pause. Okay, so if I want to do this problem, I'm going to convert it first to grams. We're going to then divide each one by its molar mass on the periodic table to get both of them into moles. Doing that gets me a number of moles. Then I'm going to divide by the smallest number. So I'm going to divide both of them by 1.33. Doing that gets me a 1. This one comes about like 1.5. And when I have something that doesn't come out to be a whole number, remember, in order to do that, I can like multiply by some number. So for this one, I'm going to choose a 2. And when I do that, then I have the ratio of those two atoms, which I can then write as a formula. Okay. For the next one, given an empirical formula and a molecular weight. So let's say I had this V2O3 as my empirical formula. If I'm given a molecular weight of, let's say, 3 times that, then I can determine what the molecular formula is from that molecular weight. And so I don't, just 1 second. I'm actually going to do the math here. Give me 1 second. Okay, so I've given you the empirical formula from the previous problem and the molecular weight of the actual compound. So this is like of a molecular compound. I'm trying to figure out what the final molecular formula is of a compound that's related to this empirical formula. So in order to do this, I need to know the molecular weight of my empirical formula is 100 and... Oops. Sorry for the drama. Okay, so the molecular weight of this V2O3 empirical formula is 150 grams per mole. I know that the molecular weight is 300, so if I do a molecular formula divided by empirical, I'm going to get, in this case, 300 over 150 equals 2, which means I'm going to take the empirical times that ratio. In this case, it was 2. And I'm going to make a new formula to represent the molecular formula. Okay. Okay, so the last 2 slides involve limiting reactant. So where we are given, let's say, any reaction that occurs. This is the one I always go to because it's kind of the simplest one for me to remember. But if I say 50 grams of O2 react with 5 grams of H2, and I'm trying to figure out which is the limiting reactant, then I'm going to go through and I'm going to take that 50 grams of O2 and I'm going to convert it to moles of O2. And then I'm going to convert that to moles of H2O. Oops, sorry. Because the goal here is going to be to figure out how much of H2O can be produced. So in order to do that, I have to take both of these things to H2O. And then if I want to know grams, then I have to go to grams of H2O by multiplying by our molar mass. And in order to do this specific problem, could have given myself easier numbers. I see that I am producing a smaller amount of O2, but I'm still going because I have to do a molar, whoops, apologies. I don't know. I don't even know what I don't know. Jeez, apologies for that. Okay, so going from moles to moles, in this case, I've got to use a mole ratio. Whichever one produces the least amount of moles is going to be my limiting reactant, but it has to be of the same thing, right? So I can compare moles of H2O to moles of H2O, but I cannot compare moles of O2 to moles of H2. Those two things are not identical. So going from moles of H2 to moles of H2O, I'm going to use a mole ratio of 2 to 2. Because that's what my coefficients say, remember? Going from O2 to H2, I'm going to do a 2 to 1. That's going to give me 3 moles of H2O, and this one's going to give me about 2.5 moles of H2O. So because of that, I now know that my H2 is going to be my limiting reactant, which when you reacted them, you probably didn't necessarily know that that was going to be the limiting reactant. We don't want to make assumptions based on numbers we're initially given. We always have to do the math. And then if I wanted to, I could go to grams, of H2O by multiplying by the molar mass of water. The last two are literally to do what we just did. So in that previous problem, our limiting reactant then is defined as the thing that produced the least amount of H2O, which in our case was the 5 moles or 5 grams of H2. It produced only 2.5 moles of H2O versus the 50 grams of O2, which actually produced 3 moles. And then the theoretical yield is the actual amount of the H2O produced. To calculate the percent yield, we need a actual yield. So this is like experimental amount or a given amount. We need the theoretical yield. This is our calculated one. And then we multiply that value by 100%. So that's one of the formulas that you'll be given on your exam. All right, that concludes chapters 1 through 3. I apologize for some of the jerkiness. It's been a while since I filmed the video, and this tablet is just not loving me. Thanks. That's it on the first 3 chapters.